direction with some phase. It's easy to prove that this, you can start with any phase and it all comes out the same in the end. This phase I'll choose to be 1. So it just comes out that the time reversal of the up spin is the down spin. Yeah. Now the time reversal of the negative z spin is a phase times the positive z spin, of course. And we're going to show that the phase must be negative in just one moment. Because let us consider the linear combination, which is plus and minus. This should have been plus z and minus z if I wrote that out so carefully. If you superpose equally this one and this one, you'll get the state representing positive x. If you do them with opposite sign, you get the state negative x. All that should be known to the elementary student of spin. Now let me suppose that I try to say that the time inversion of minus z is the state plus z without that minus sign. Then do you see that the time reversal of the state plus x, this plus will go to minus and this minus will go to plus, will produce the same state again, which is not right. It's supposed to produce the opposite state. And therefore, I have to change the sign here. Otherwise, when I did the time reversal, I would produce the same state. Well, if you put the minus sign in there and watch what happens, the plus goes to minus and the minus goes to minus plus. If you can understand such a horrible thing. And if you look at it a bit, you'll find that that's the negative of the spin in the minus x direction, and that's where the negative is just a phase, and the spin in the minus x direction is what we want to reverse. Hence, it's necessary with spin a half that if the time reversal of the plus state, up state, is the down state, that the time reversal of the down state is minus the up state. It's so much fun. Now we do it again, huh? Well, we just learned that the time reversal of the down state was minus the up state. And here we learn that the time reversal of the up state is the down state. Now to keep this minus sign going through. So you see that if we do 2 time reversals, we change the sign. So it's just necessary. And there's nothing, it wasn't in space, but we did it 2 reversals of spin, 2 time reversals, and you change the sign. It's equivalent to, it's just what you would do if you rotated 360 degrees. For a particle of even spin, which can have a state with a component along the z-axis of 0, the time reversal of that is still 0 along the z-axis. Any positive spin will turn negative, but the 0 will be 0. So therefore, the time reversal of this state, some j that's even, I mean integral, with the m equals 0, will be some phase times the state with the m equals 0. But if you do the time reversal again, I got the time reversal of this is e to the minus I phi times the time reversal of that, because of this alpha star. But the time reversal of that is e to the I phi, and these phi's cancel out, and you get the j m equals 0. So therefore, 2 t's on a integral spin is plus 1. In other words, 2 t's has the same effect as a 360-degree rotation. Okay. It's minus for spin is a half integral spin, and it's plus for integral spin. How did I get here so fast? Okay, then I got them in the wrong order. Nope. Now when we look at the sign of a loop, I'm going to talk about the loop that had the contribution that was supposed to stop the vacuum. You remember, if you have a potential present, you can produce pairs. Therefore, the probability that you don't produce pairs must be less than 1. And you have to get the sign of the loop right so that 1 plus those loops is less than 1. In other words, the real part of the loops must be negative. And what you have to do that is when you have Bose, you have 2 particles coming out and going back into the same state. You have to have exactly the same thing with the positron and the electron going out and coming back in the same state, as indicated here. And I've written it out more carefully here. The amplitude is 1 plus x, where x is the contribution from this loop. Its real part times 2 must be negative and cancel the probability of pairs are produced, so that the sum of the probabilities over all alternatives remains unity. And that's going to determine the size of the thing. Now, to get the sign of the positron propagation to be right, just like a particle going from a state to the same state, we saw that we have to multiply by an extra TT. Otherwise, we'll have the wrong contribution of positron, have that extra minus sign. In other words, we have to multiply by -1. That is, the x is the loop trace times -1. One way of seeing it is that the way you want to go, coming out and coming back, is to change the time once and change the time again as you go around the loop. And that changes the sign. I pointed out earlier if the loops had -1 that we would have family statistics, because you have 2 loops or 1 loop, and if there's a minus on each loop, when you made the exchange, you change the sign. It's interesting to realize that when people first figure out this loop, there was an ambiguity that no one seems to have worried about. It goes something like this. You're supposed to start in some state and then propagate around with all the couplings and everything else. And then they ask, are you in the same physical state? And everybody puts the U bar there, the U conjugate or whatever, and sums over all states. That becomes a trace. But the same physical state might be minus U. Maybe we've turned by 2 T's, and indeed we have, because in order to get this the way we want it, we have to have the 2 T's in succession. And so it should have been minus U that we multiply. In other words, we have minus the trace of the propagator. The kind of a circle that I mean here is that 2 particles are coming out in some state and coming back in the same state. I can represent that, if my pants don't fall down, by a belt of this kind, where this one went around one way and this went around the other way. But you see that that is 2 time reversals. It's a 360-degree rotation. And so when there's an odd number of pairs of T's, I count that as 1 TT, okay, an odd number of 360s, the contribution should be positive. That's the case I want. And when there's an even number of TTs, there's extra TT in it, the contribution should be negative because the extra TT makes it negative. This signs plus and minus are relative to what happens with the Bose case, in which they're always positive. So what we have discovered is that we have to put a minus sign in front of the traces of the propagators for the spin-a-half particle, and therefore that produces, as indicated before, a minus sign between 2 diagrams. I think I have another picture of those where you have 2 loops or 1 loop, and the minus sign comes twice with one case and once with the other. When you exchange something connected with 2 loops, it becomes 1 loop. Mr. Finkelstein, David Finkelstein, always makes the following demonstration, which bothered me for a long time because it sounded like it was very important, but I couldn't get all the signs right and straighten it out. But suppose you have 2 loops. I can't make it out of 1 belt, but you imagine the other one here. And instead of connecting them that way, I connect them crosswise. You see here, this goes over to the other loop, and this loop comes over to this side. Right? And you put them together. How many turns do we have? Okay. Well, you see there's an extra one in there. The loop I wanted went around straight. That's the plus one. If it has an extra turn, it's minus. And so this one's minus to what you would have expected. And that's the reason for the sign change when you exchange the particles. If you want to understand that it really is 2 turns, you try to get, if I can ever get it back to where it was. Yeah, well, here's the way it was on my arm, I think. And you see that if you go around once, twice, you see. T, 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 which is 4. And there's 2 extra T's, and there's a minus sign. So everything's okay, and I think I understand Mr. Finkelstein's demonstration now. Finally, I would like to show you an example in which we have a spin-a-half object in which we know where the angular momentum comes from. And that's fun. Suppose that we had a thing that Dirac invented, and it's therefore appropriate in this lecture, a magnetic pole. And suppose we have a charge Q, and we'll suppose that these particles, the magnetic pole and the charge, are both spin zero. So we don't have to worry about any intrinsic angular momentum of either of those two things. But they're in each other's presence. And here's the magnetic pole and here's the charge, and there's springs from one magnetic field in all directions and from the other electric field in all directions, and they cross each other and make a pointing vector, which is momentum, which goes around this way, and sure enough, the thing has angular momentum. And the angular momentum is independent of how far apart they are, because if you started this way and moved them